Welcome to another unit in the workbook Statistics. This time we're going to focus on the so-called normal distribution. The normal distribution is, I would say, the most commonly used and most important distribution in statistics, also because a lot of other distributions are based in one way or another on the normal distribution. Mathematically, we can write it like this. And if we look closely, we see that there's two parameters here which impact how it looks. That's on the one hand here the mean, the average, and down here and over here the variance. So those two statistics tell us what our specific normal distribution looks like. That's just pi, which is 3.14, so forth. And we also see it's an exponential function with a minus here and with a square here. That's what gives it this shape. The values are rather close to the mean and there's going in both directions in the same way. So it's a symmetrical distribution with the mean being exactly in the middle. The variance, or rather the standard deviation, also tells us something about it. That's more or less how many observations are covered if we go with plus minus 1, 2 or 3 standard deviations. Well, that's already pretty interesting to know, but how can we work with this? Well, normally if we have a continuous distribution like the normal distribution, we would simply start by calculating the integral of this function. There's, however, one big problem. We cannot get a closed analytical solution to the integral over this function. So what we do instead is we're going to standardize our values first. Standardization in this case will eradicate the mean and the variance. Standardization always means we subtract the mean, we're going to divide by the standard deviation. If we use standardized values, we always get the so-called standard normal distribution with a mean of 0 and a variance or a standard deviation of 1. That's actually pretty neat, because in this case we only need to have one single normal distribution. We need to know something about a single normal distribution. That's really helpful because, as I said, we cannot calculate this the integral over this function in a closed form. So what we do instead is we calculate mathematically, we approximate mathematically the values for the integral of that function. Well, if we were to build such a table for any combination of means and variances, we would have a lot of tables. However, if we actually only have to use a single distribution, the standard normal distribution, then we can prepare one table which covers most of the important values in this regard. Also, well, as we see here, with plus minus 3 standard deviations, we cover most of our observations. We are pretty close to almost 100%. So we do not need this large of a table because with very small values, we already can cover a lot of area. Also, next part, we only need half of this because, well, it's symmetrical. So if we know how it looks on the left, we already know how it looks on the right. That's why those tables always start at 0.5, at 50%. We're only taking a look at one side. Well, the mean, as I said, is always 0. That's why the values start, when we start at the mean in the middle, starts with 0. So we're not considering negative values because, well, we only consider this area. If we know anything about this area, we also know this about that area. So it's actually a pretty neat help to save a lot of work, a lot of, well, space regarding these values. So we just need to find the respective value, the respective standardized value, and then we can look this up in the table for the normal distribution, for the standard normal distribution. That again is how it would look like. As I said, we cannot calculate this integral. Well, aside from these general facts on the normal distribution, I want to mention a few rules which make the calculation of probabilities a bit easier, building on the properties of any normal distribution I just mentioned, in particular on its symmetry. First, I'm going to copy this value, and then we take a look how we calculate probabilities. Well, we know probabilities as in probability of x being smaller than a certain value k, can be calculated for continuous distributions by inserting the value k or x into the distribution function. We also know the distribution function we want to use here is the distribution function of the standard normal distribution, which is this large phi here. To get any value here, we first have to standardize it. So that's actually what we're going to do. We standardize the values, and then we're going to insert them in the distribution function of the standard normal distribution into this big phi. This big phi is actually the table I introduced on the slide before. Well, aside from this, I mentioned before that those tables only contain positive values. We do not need negative values because, well, if I know I'm up here on this side with the positive value, I know I will be on this side with the respective negative value on exactly the same level. So this function is symmetrical. This means that this applies for probabilities as well. So I could change a negative part here into a positive part like this. Or, well, if I go and say it should be larger than this value, I could also say, well, it's 100% because the area is 100% minus all the rest here. So probability of x being larger than that value is the same as 1 minus the probability of it being smaller than this value. That's actually this rule. So instead of looking up a negative value, we simply go with 1 minus and then look up the positive value. Similarly, if we want to calculate the probability of x being inside a certain interval from a to b, we can use something which we know about the calculation for integrals. So we're first going to insert the upper boundary, calculate the probability here, then minus inserting the lower boundary. Well, this also can be explained with this graph. If I want to know what's the probability of this area, x being between these two values, first thing I'm going to do is calculate the area left of this part here. So this part here. Then I'm going to subtract the area left of that part. I'm left with the area here inside this middle part. So it's actually pretty straightforward. Then finally, there's this one rule which also uses symmetry. If I'm going to calculate, for example, the probability of being larger than or smaller than that one, larger than that one, and those two values being equally wide away from the mean, then we can use a slightly even more, well, easy version of this formula, because then those two values after slight reformulations will be exactly the same. Well, this works with this formula for being outside a certain interval. If we just go with 1 minus this, we could also turn this around and say, well, we're inside this area, but inside an area which borders are equally wide away, further away from the mean. So for example, plus minus a certain value. Well, that's everything I wanted to mention with regard to working with the normal distribution. Certain rules about this, which might make calculation of probabilities a bit easier. So I hope you enjoyed this session. I say goodbye and see you next time.